Welcome back. So in part 2 of my lecture, I'm going to introduce a new tool for classifying elliptic curves. And actually, this tool, the discriminant, is something that can work for any polynomial equation. So to make things simpler and try to motivate what makes this formula a useful thing, let us reinvestigate quadratic functions, right? So these will be a little bit simpler. We know how these work. We know how to solve them. My equation is going to be y equals a times x squared plus b times x plus c. X and y are still my variables, and a, b, and c are my constants. So I hope that you remember the quadratic formula. If not, I've got a copy of it here on the screen. The quadratic formula is really great because no matter what these numbers a, b, and c are, I can immediately calculate the solutions to the quadratic equation. And there's only going to be 2 of them. So the quadratic formula says my solutions are x equals negative b plus or minus the square root of b squared minus 4ac. And that's all divided by 2 times a, right? So I won't sing the song for you. I claim the most interesting part of this formula is what happens underneath the square root, right? I can take a negative b, I can take a 2a, that's just sort of bog standard. But the behavior of my solutions ultimately comes down to what I've got under that square root sign. So there's only really 3 things that can happen when I'm comparing 2 real numbers. Well, one could be bigger than the other, right? One could be smaller than the other, or they could be exactly the same. And those 3 possibilities are going to give me the 3 possibilities for the solutions of a quadratic. So if b squared is greater than 4 times ac, right, I take b squared minus 4ac, that'll have to be positive. The square root of a positive number, that exists, it's positive, so I'll have 2 real numbers that are the solutions of my quadratic. I'll have 2 different solutions. Another possibility is that b squared could be less than 4 times a times c. So in that case, b squared minus 4ac will be negative, and I'm taking the square root of a negative number. And that puts me back in the world of complex numbers. So I cannot square a real number and get something negative. I need to square an imaginary number. So if my b squared is less than 4ac, or rather, if my b squared minus 4ac is negative, I have complex solutions instead of real solutions. And I'll have 2 different possibilities, one for plus the square root and one for minus the square root. I'll have 2 different answers. The last possibility is what happens if these 2 things are equal to each other. If b squared is exactly equal to 4 times a times c. For my quadratic formula, I'm taking the square root of b squared minus 4ac, and I said that those are the same number, so I'm taking the square root of 0. That's not so bad. Square root of 0 is 0. I can do that. But 0 is the only real number where plus and minus get me the same answer, right? Negative b plus 0 and negative b minus 0 are the same number. So there's only one real solution here, right? It's going to be negative b on 2a. And Way back when we were learning polynomials, years ago at this point, we called this kind of a solution a repeated root. Because if we were going to factor the quadratic, we'd get the same root twice. But there's only one place where it touches the x-axis. So the formula b squared minus 4ac, which we've known as part of the quadratic formula, this by itself is called the discriminant for quadratic equations. So whether this discriminant is positive or negative or zero tells us what the solutions to the quadratic equation can look like, right? It all comes down to calculate this number based on the coefficients a, b, and c we started with, see what we get. Whether or not that is zero tells us if we get one or two solutions. So there's an entire theory of discriminants, which I'm not going to get into. I want to allude to it. It's handy to know that this stuff is out there. Depending on where you end up, it might be useful to use discriminants for computational purposes. So know that they exist. The theorem here is that every polynomial has a discriminant. That's part one. Every single polynomial has a discriminant, and we have ways of calculating that formula. So if you want to know, what do the discriminants tell us? If you want to know what the discriminants tell us, we need part two of the theorem. The polynomial we're looking at has repeated roots if and only if the discriminant is equal to zero. So the first job of the discriminant is telling us whether or not the polynomial has repeated roots. Again, they can tell us some more interesting stuff in general, but we don't need that right now. We just want to know, do we have repeated roots or not? So with this tool, I just want to be explicit. The quadratic discriminant is the formula b squared minus 4ac. You calculate this. If you get 0, your quadratic has repeated roots every single time. Okay, so I claim that these exist for every single polynomial. Let us return to the cubic I was looking at in the first part of today's lecture. So my cubics have a special formula. They are always going to be y equals x cubed plus ax plus b, right? If this was a squared, if this was y squared, I'd get an elliptic curve. I want to understand the cubic that is influencing my elliptic curve. And for that reason, I'm always going to be using this formula. So it'd always be 1 times x cubed, 0 times x squared, some constant a times x, and some constant b. This is sometimes called the Weierstrass form of an elliptic curve. It's just a handy way to be working with cubics. One of the major benefits, and this is one of the reasons I will only be using this kind of formula, is that the discriminant is very easy to calculate for cubics with this formula. So if you have a polynomial, x cubed plus ax plus b, I will tell you that the discriminant of that polynomial is the formula -4 times a cubed minus 27 times b squared. So this is just some number I can calculate based on the coefficients of my cubic. And I claim that if this formula is 0, the cubic has repeated roots. There's some place where I can factor out the same solution 2 or maybe 3 times. Okay, so that's a lot to chew on. I want to return to my graphs. So I have another Desmos link. You can copy the URL into your browser. Here it is again. You can also find it on the slides and just click on it. So let us see my cubic setup from before. Now what I've done might be a little hard to see here. In red, I have the formula for my same cubic as before, y equals x cubed plus ax plus b. And a and b are my constants. I don't have a slider for a anymore. That's all right. I still have the slider for b. What I've done is that b is a free parameter, right? This is still a slider. It still influences my elliptic curve the same way. But I've introduced a new parameter, capital D, and D is the discriminant. So the reason for this formula here is that I get to pick my discriminant first, and then I get to pick my value of B, and this formula just calculates the correct formula for A so that this curve has capital D as its discriminant. So here I have D equals to 10, which is not 0, and I can confirm that my curve in red does not have repeated roots. What does it look like to have repeated roots for a cubic? Let's set D equal to 0. And right here at x equals, oh, I just had it there, 0.79, I think it is a double root. And I can tell that this is a double root because it touches the x-axis and then moves away from it again, just like the parabola y equals x squared. In fact, let me stack the deck a little bit. If b is 0 and d is 0, then a is also 0. So this formula, y equals x cubed plus 0x plus 0, is just the same as y equals x cubed in blue. They are exactly the same formula. And this is a triple root, right? So I've only got the one solution for x cubed equals 0. X has to be 0. But it's a repeated root because I can factor this as x times x times x. I can play around with my b parameter. Here's some negative values of b, and I've got this double root right here, again because I fixed my discriminant to be equal to 0. I can have a positive b, and now my double root is over here. All of these curves are going to have double or maybe a triple root. And I only get the triple root for b equals 0. There it is. Now, what is the point of the discriminant for elliptic curves? I'm going to keep on having elliptic curves with discriminant 0, so I'm going to leave this slider alone. Let me pick some random value here. For my underlying cubic, right, I know that my elliptic curve is not going to go any farther than about negative 2.1 here, because again, I can't have negative y squared. And I'm going to have this sort of bulb going on here, and it's going to get narrow again and come back to the x-axis and then move away, right? I can start to imagine what my elliptic curve is going to look like. Let me go ahead and turn on the graph of the elliptic curve. There it is in purple again. And let's get rid of the cubic so I can see this a little bit better. And here is something that I have not seen so far. My elliptic curve loops around and crosses itself. And I can pick whatever b value I want, fixing the determinant as 0, and all of these elliptic curves cross themselves. So this discriminant, the fact that negative 4a cubed minus 27b squared is 0, the fact that that discriminant is 0 shows me, algebraically, that my curve is going to intersect itself. Again, every single time. And I can flip around and we've got some other kind of behavior here. So a bit of a lie, right? What happened for these? Let me turn my cubic back on so we can see it. Here, my double intersection is happening in a place where the elliptic curve is not defined, right? My x is giving me negative values for the y coordinates of the cubic, and those do not show up on my real graph. Now, I've already alluded to this in the talk. When we're trying to take the square root of a negative number, right, that puts us in the world of complex numbers. And I claim that there's actually a self-intersection of the graph of the elliptic curve, but it is a self-intersection. It's going to cross itself when I plot it in imaginary coordinates instead. So, a bit of a lie. I can have a zero discriminant. It doesn't look like I've crossed myself in the real xy plane, but there's going to be some hidden stuff going on in the complex plot. We are not going to be terribly concerned about that, so it's all right. My final example is going to be this particular elliptic curve. So here my discriminant is 0, my b is equal to 0. Once again, that's just drawing the curve y equals x cubed, or here y squared equals x cubed. And for this graph, and this one alone, I get this point, right? So it looks like I'm about to loop around, but then I don't. So I have this sort of point on the graph, like literally a corner, not an xy coordinate. So with a slightly bigger value of b, you can see I've got this extra bulb. The graph comes down here, loops around, and crosses itself. If my b is exactly equal to 0 in this situation, then it just stops at a point right there. So the main point of this mini lecture is that I can predict the shape of my elliptic curve just off of the formula minus 4a cubed minus 27b squared, the discriminant of the cubic. And I could also call this the discriminant of the elliptic curve. So if this is 0, we have a possibility of self-intersection. Sometimes that self-intersection will be shunted off into imaginary land and we can pretend like it doesn't exist. And other times we will see that self-intersection directly here on the real xy plane. So the major takeaway for this, beyond being able to determine self-intersections, is that I don't want this to happen with the elliptic curves that I'm working with. So we will see in tomorrow's lecture that we can use these kinds of graphs to build a group. And that is the elliptic curve group. And that group is going to allow us to make a new system of cryptography. The problem is, for that group to work, we do not want these self-intersection points. For right now, that just means we do not want a discriminant of 0. So I'll say that one more time. for elliptic curve cryptography, we do not want an elliptic curve whose discriminant is 0. But fortunately, that is a super easy test to calculate. We just take the constant a, we take the constant b, we put them into the formula, and if that is 0, okay, we got to throw that elliptic curve away. If we get anything besides 0, then we are in business. And again, discriminants can tell us a little bit more, but for right now, I'm okay with just saying avoid discriminants 0. Okay, so those are my two big definitions for today. Elliptic curves from the first part of the lecture, and now discriminants in the second part of the lecture. So make sure that you know the formula minus 4a cubed minus 27b squared. But besides that, all we're looking at is just the graphs of some polynomial equations. We'll see how the geometry involved can actually let us get a group starting tomorrow.